Welcome to Mr. Tompkins EdTech and my series of exam question compilation videos on key topics you might still be struggling with. This particular video covers circle theorems. I've taken related questions from my past paper walkthroughs and given them to you here back to back. These compilation videos will give you a deep dive on topics you are still finding challenging, giving you more of an overview, helping you recognise command words, identify key features and strategies, building your confidence and helping you apply these techniques for future papers. If you find it helpful, please give the video a thumbs up, it will really help me out. Also, if you haven't already subscribed to my channel, why not do that now? I'll be making lots of these compilations over the next couple of weeks and you'll get notified of these as soon as I upload them. Right, let's get into it. Question 12, we've got a circle theorems question. The blurb at the top says A, B, C, D, E and F are points on a circle, and indeed they are. No other information to add to my diagram. Circle the line that is a diameter to the circle. Okay, now for it to be a diameter, what we want to be able to do is use our circle theorem that involves a diameter. So if I've got a diameter and I subtend an angle in it, then this one here will be a right angle. So I can use that to work out which is going to be the semicircle. So I'm looking for a 90-degree angle. So in this first triangle I've got 5 and 95. So working out the third angle of that one is going to be 180 take away 95 take away 5, so 180 take away 95 and 5, which is 100 taken away from 180, so that one's going to be equal to 80, isn't it? So that's 80 degrees. So that one isn't the diameter. This other triangle here, what's this angle here then? So this one would be 180 minus 80 and 10. 80 plus 10 is 90, and 180 take away 90 is 90. So that's my right angle there, isn't it? So because C is a right angle, that means that AD must be the diameter. So that one. Question 12. A, B and C are 3 points on a circle. The radii from A, B and C are shown. Is AC a diameter of the circle? You must show your working. Okay, so it's not drawn accurately, but we've got 3 angles given, and we need to see if 5x plus 40, then this one here resolves to 180 degrees. And if it does, then AC is going to be a diameter. But if that angle is not 180 degrees, then it's not a diameter, is it? Okay. Now, we've got 3 angles meeting at a point, basically. So we've got 5x plus 40, we've got x, and we've got this 2 lots of 2x plus 20, okay? And we know that angles meeting at a point sum to 360. So angles meeting at a point sum to 360, okay? So that means those 3 angles added together should be 360 degrees. So the 5x plus 40 plus the x plus the 2 lots of 2x plus 20. So the yellow one, the green one, and the blue one added together should be 360. Okay? So let's try and collect everything together. Before I do that, I'm going to have to multiply out this bracket here, aren't I? Okay, so I might collect the 5x and the x together. So that's 6x plus 40 plus, I've got 2 lots of 2x, which is 4x, and I've got 2 lots of 20, which is 40. So that's equal to 360. And then I've got my 6x and the 4x, and I've got 40 and 40. So adding those together, that gives me 10x plus 80 equals 360. Okay, So I've got a linear equation in x. Let's go on and solve it. Let's take 80 away from both sides to start with. That will cancel, and it'll leave me with 10x on the left. 360 minus 80, that's 280, isn't it? So then if I divide both sides by 10, cancel, leaves me with x is equal to 280 divided by 10, that is 28 degrees. Okay, now I've not answered the question, have I? The question was, is the yellow angle a straight line? So therefore AC is a diameter. So if x is 28, then 5x plus 40 then is going to be 5 lots of 28 plus 40. 5 lots of 28 is 140, plus 40 is 180. Okay, so that means that that angle is 180 degrees, which means AC must be, therefore AC is a diameter. Question 13. The diagram shows points A, B, C on the circumference of a circle. Line DAE is a tangent to the circle. DE is parallel to BC. Prove that triangle ABC is an isosceles triangle. Give the reason for each step of your proof. Okay, so what do we know? Right, so this triangle ABC is going to have 3 angles, isn't it? It's going to have one here, one here, one here. Okay. Now this one up here is the same thing as what? What do we know about it? Well, we've got a pair of parallel lines, haven't we, and a line crossing them. So that angle there is alternate to this one down here, isn't it? So that one is the same. Okay, so we're just going to label, you colour it in the same colour. Okay. What else do we know? We've got another angle over here. Okay, using the same logic, that is going to be the same as this angle down here. Okay. However, we also know something called the alternate segment theorem, which says the angle between a tangent and a chord drawn at the point of contact is equal to the angle in the alternate segment. So actually that angle there is the same thing as this one up here. Okay, so that means all of these are the same. Okay, so then I've got 2 angles the same up here, which means this is going to have to be an isosceles triangle then, isn't it? Okay, that's my thinking. Now I need to write that down. So how did we start? And I think I actually went too far. I don't think I needed to go quite so far. I think what I can do instead is I'll go from this one, knowing this one, to knowing this one, and from this one, knowing this one, to knowing that one up there, and then look, then they're equal to each other. I'm done. So I actually did more thinking here than I needed to. I don't need to think about that one. Okay, so starting with this angle up here, BCA. I'm going to start with that angle, and we said that that angle was the same thing as this one down here, due to rules about parallel lines, isn't it? It's the alternate angle in a pair of parallel lines. So that's what we can say first then. We can say that angle BCA is equal to angle CAE. And the reason for that is alternate. The alternate angles. Okay? And then what can I say? I can say, but CAE is equal to, well, next thing we said was this angle here is the same thing as this one up here, isn't it? So the angle between the tangent and the chord is equal to the angle drawn in the alternate segment. So that angle there, look, is equal to that one. So CAE is equal to ABC. And we know that from the alternate segment theorem. Okay, alternate segment theorem. Now, so that tells me that BCA equals CAE, which equals ABC. Okay, in other words, BCA equals ABC. Okay, and that means triangle ABC is isosceles. Okay, that's it. Question 13. Points A, B, C and D lie on the circumference of a circle. Line AC intersects line BD at point E. Prove that the triangle AED is similar to triangle BEC. Okay, so similarity means same angles. So what we need to show then that the three angles in AED match the three angles in BEC. Okay, so can we do that? So where are these two triangles first? So triangle AED is this one. So we need to find the three angles of this one compared to the three angles of this one. Now obviously we don't have any angles written on here, so we're going to have to give them angles, I guess. We could call them X, Y, and Z or something, and then show that they're equal to each other. Okay, let's start with the angle at E, because that one's fairly straightforward, isn't it? So here, what we've got is two vertically opposite angles, haven't we? So these two vertically opposite angles must be equal to each other. So I'm going to start with that. I'm going to say angle AED is equal to angle BEC because they are vertically opposite. Okay, so those two are equal. So then we've also got angles subtended from the same point. If you think about it, angles A and B, so the angle up here and up here, these two have got to be equal to each other as well because they're subtended from the same chord or arc. So they're both subtended from this chord here or arc here, DC. So they're both subtended from the same chord. So I'm going to say that DAE is equal to CBE, and the reason is because angles in the same segment subtended from same chord. Okay, and then finally we could say the same argument for the other two angles at the bottom here then. So this angle here and this angle here, they're both subtended from the chord AB, aren't they, or from the arc AB. Okay, they're both subtended off that same chord. So those two got to be equal to each other as well. So that angle there is going to have to be that angle there. So we can say then that ADE, angle ADE, that is going to be equal to BCE angle for the same reason. So that means that all of the angles match. Therefore, all three angles in both triangles match. So must be similar. Okay. Question 16b. M, N and S are points on circle C1. So you can see they're all on the circumference of that circle. RST is a tangent to C1, and circle C2 passes through the center O, S and M of circle C1. And we need to prove that SM is not a diameter of the circle C2. Okay, so where is SM? SM is this line here, isn't it? Okay, there's my line SM. Now, if it was a diameter, then it means it would pass through the middle of the circle. And it also means that any angle I subtended from it would have to be a right angle, because an angle subtended in a semicircle is a right angle. So if SM was a diameter, then that would have to be 90 degrees. Now, if that was 90 degrees, then this angle here must be half of it, must be 45 degrees. But is it? I don't think it is, because I've got a tangent here and an angle subtended between that tangent and a chord. So then the angle subtended in the alternate segment must be equal to it. So that angle up there must be 48 degrees. So if that is 48 degrees, then that center angle there is going to be twice as big. 48 times 2 is going to be 96. I don't want to keep writing in blue. So that angle there must be 96 degrees. And therefore SM cannot be a diameter because it's not a right angle. Okay, so we need to write that all down now. So let's start with let's work backwards. So let's start with the tangent and working out what the angle at N is. So RST is a tangent, and therefore SNM, the angle, must be equal to 48 degrees because of the alternate segment theorem, which means then the angle at the center, SOM, is twice that. It's going to be 48 times 2, which is 96 degrees, and that is because angle subtended at center are twice angle subtended at circumference. So you have to learn these rules really, so you can write them down like this, and then so now we're saying that SM, if SM was a diameter, then SOM would be 90 degrees, and that is because of angles in a semicircle are right angles, and it's not, and it is not. So SM is not a diameter. Question 20. PQ, R and S are points in a circle. PXR and QXS are straight lines, and we're told that PX is equal to SX. Okay, so we need to prove that QS is not a diameter of the circle. So if this is not a diameter, then it doesn't pass through the origin. And it also means that if I subtend a angle off of it, like this angle up here, then that is not going to be a right angle then, isn't it? So I think that's basically what we need to do. We need to find that angle OPS and show that it's not a right angle. Because if it was a right angle, it would imply that QS was the diameter. So that I'm subtending a triangle, an angle off the diameter and giving myself a right angle. Okay, so I'm just to make that super clear, if I have got an a diameter passing through the origin and I draw an angle off of it, that one will always be a right angle. So if I find that OPS, this angle up here, isn't a right angle, then that cannot be the case, and therefore QS is not a diameter. Okay, so that's my plan of action. I'm going to find QPS. Now we can see that QPS is made up of two smaller angles. It's made up of that one there and that one there added together. So this is a isosceles triangle. So if I can find that one, then it must be equal to the other one. Can I find that one? So because the top of that isosceles triangle is 50, then this one is going to be 180 minus 50 divided by 2 then, isn't it? So 180 take away 50 is 130, and 130 divided by 2 is 65 degrees. So that one there is 65 in there, which means this part over here, RPS, must also be 65 degrees. Okay, so we've got half of the green angle. Now we need to find the other half. Now we can know that that half is the same thing as this angle here, 27. So that one is going to be 27 because of it's subtended off the same arc QR. So we're going to write all that down now. So 27 plus 65 is not 90, is it? It's 85, 92. So it isn't a right angle, and therefore it isn't going to be an angle in the semicircle. So I'm going to write all that down then. So I'm going to say that angle XSP, is equal to, we said it was 180 minus 50 over 2, which is 65 degrees. And the reason for that is angles in an isosceles triangle okay, so now I knew that one is XPS, and so I also know that the other angle XPS is equal to that as well, so they're both equal to each other. So XPS is the angle we were actually trying to find, wasn't it? And then QPR, angle QPR, I'm saying is equal to angle QSR, and that is equal to 27. And that is because they are angles subtended from the same chord QR. They are equal. That's the rule. Okay, so angles subtended from the same chord QR are equal. They're equal to 27. So then my angle QPS, so my angle QPS is going to be those two angles added together, then, isn't it? It's going to be angle XPS plus angle QPR. And that is equal to 65 plus 27, which is equal to 92 degrees. So we found that QPS is equal to 92 degrees. And we're saying that's a problem now because it should be 90 degrees if it was angles in the semicircle. So if, what side was it? It was QS. If QS was a diameter, QPS would be 90 degrees because angles in a semicircle are 90 degrees. And it isn't, it's 92, isn't it? But as angle QPS equals 92, then we can say that QS is not a diameter. Okay. So I've been clear there exactly what angles I've found and also why I don't believe QS is a diameter, and that should be enough to get me all 4 marks. Question 20. A, B and C are points on a circle. CD is a tangent, and underneath the question it says, assume that the triangle ABC is isosceles with AC equal to BC, prove that AB is parallel to DC. Okay, so assume that triangle ABC is isosceles with AC equal to BC. Well, AC is that length there, and BC is this length here, isn't it? Okay. Now, right, coming back to the diagram, if CD is a tangent, then we can use the alternate segment theorem to state that that angle there, the angle between a tangent and the chord join at the point of contact, is equal to the alternate angle. So the angle drawn in the alternate segment, that one there. So this angle and this angle need to be equal to each other. Plus, of course, in triangle ABC, if it's an isosceles triangle, then we can say that the base angles are equal. So then this angle up here must also be equal. Okay, so we've got 3 equal angles now. Okay, now if CD and BC are parallel, then this line here, the line AC, has got to be a transversal, then a line crossing 2 parallel lines, and this angle in here and this angle over here should be alternate and therefore equal. Okay, so if you've got 2 pairs of parallel lines and a transversal, then these 2 angles, the alternate angles, are equal. Another way of saying that is if these 2 alternate angles are equal, then the lines must be parallel because you've got alternate angles. So it works both ways. Parallel lines implies alternate angles also imply parallel lines. Okay, so we need to write that up. So we said using alternate segment theorem, we showed that angle ACD was equal to angle ABC. Okay, and then because base angles in a isosceles triangle are equal, and that means that angle ABC is equal to angle BAC. So BAC is equal to angle ABC, which is also equal to ACD. They're all 3 of them are equal to each other. And then we can say if AB is parallel to CD, then AC is a transversal and angle BAC is alternate to AB to the other one. What was that? ACD. And therefore BAC should be equal to ACD. Hence AB is parallel to DC. Okay. 20b. In fact, triangle ABC is equilateral. Tick the 2 boxes for the statements that must be correct. AB is parallel to DC. AC bisects angle BCD, or AC bisects angle BAD. Let's go back to our diagram and add in the extra information. So if it's actually not an isosceles triangle, it's an equilateral triangle, then also that length is equal, and also that angle is equal. They're all equal to 60, aren't they? 60, 60, 60, 60. Okay, so now what do we know? Let's just check each one of these in turns. Is is line AB parallel to DC? Is that true? Is AB parallel to DC? Yeah, that's not going to change that, is it? That's what we just shown before. So angle AB is still parallel to DC. Yes, that's still true. Does AC bisect angle BCD? Does AC bisect angle BCD? Oops. Where's AC? AC is the green angle. Does it bisect angle BCD? Well, if it bisects it, it cuts it exactly in half, and it does, doesn't it? Because that angle is 60 and that angle is 60, so therefore that is true. So that is also true. Does AC bisect angle BAD? BAD. Does AC bisect BAD? Is that also true on this side? Well, we don't know, do we? Because we don't know this angle here. Is there any reason to suspect that angle is 60 as well? We've got no reason to think that is the case. So I say that one is not true, or not necessarily true anyway. So I'm happy with our 2 choices then. AC, that is not the case. The other 2 are true, and we have now ticked 2 boxes of statements that must be correct. Okay, happy with those. Let's move on. 21b, C, D, and E are points on a different circle. Is X the center of the circle? Tick a box. Show working for your answer. Okay. Now, if X is the center of this circle, then this is that kind of Star Trek circle theorem that we need to know. It looks like the Star Trek badge. That's always the way I think about it. I don't know if you like Star Trek or not. But anyway, that rule says that the angle subtended at the center, this angle here, is twice the angle subtended at the circumference. Okay, so if X is the center, then the angle X is going to be 2 lots of the angle at subtended at the circumference, CED. CED is 78, so that would make X 156. Okay, is that consistent with the other angle? Angles at a point sum to to 360 degrees. So if those two angles added together give us 360, then it all kind of works out, doesn't it? So 156 plus 204, what does that equal to? That equals to 360. Okay, so it does work. Okay, so I'm going to say yes, because X is the center because of what we just argued a second ago. In 24, we've been given quite a complex diagram with a circle and lots of other angles added in, and we're asked a series of questions. We need to decide whether or not they're true or false. So first up, the first question asks, is it true or false that AC is a diameter? Now, if AC was a diameter, then ABC would be an angle. Yeah, it'd be an angle in a triangle in a semicircle, wouldn't it? So this one here would be an angle subtended within a semicircle, and it would be a right angle, and it isn't because it's 92 degrees. So AC cannot be a diameter, otherwise that angle B would be 90. So I'm going to tick false. False. Angle B is not 90 degrees. Okay, our next statement is angle ADC equals 88. Okay, where's angle ADC? ADC is this angle down here. Is that equal to 88? Well, D and B are opposite angles in a cyclic quadrilateral ABCD, and opposite angles in cyclic quadrilaterals should sum to 180 degrees. So if D is 88, does 88 plus 92 equal 180? Yes, it does. So I agree that D must be 88 degrees. So let's say that's true, and then I can say opposite angles in a cyclic quadrilateral sum to 180 degrees. Right, next statement. Is ABCD a trapezium? Where's ABCD? Okay. Well, if ABCD is a trapezium, then I should have two parallel sides somewhere. Now, to help us decide whether or not that is the case, it would be helpful to find these two angles here. So this one here and this one here. Now, using triangle ADC, which has got angles 88 and 50, I can work out that the angle at A in that triangle is 180 minus 88 minus 50, which is 42. And the other angle, I've got 92, 38, which adds up to 130, so that one there must be 50. Okay. So if I've got a pair of parallel sides, I should have two angles that are alternate in this triangle. Now obviously 42 is not alternate to 38, but these two are equal. So this 50 here and this 50 here are equal, which would imply that this side is parallel to this side. So yes, ABCD is a trapezium. So true. Alternate angles are 50 degrees. Finally, we have to say whether DE is a tangent to the circle. So here's my line DE here, and I'm told that this angle here is 32. So if this is a tangent, then the angle in the alternate segment would be equal to 32. Now the angle in the alternate segment would be this one up here, which is 42. So they don't go together, unless I've added them up wrong. Hold on. Nope, definitely 42. So no, it isn't a tangent. So I'm going to say no. And write that angle in alternate segment would be 32 degrees, not 42. Question 23. ABCD is a quadrilateral. Prove that ABCD is not a cyclic quadrilateral. Okay. So a cyclic quadrilateral is a special sort of quadrilateral. You normally see it drawn inside a circle, but if I take the circle away, it's still a cyclic quadrilateral. It's not the circle that makes it a cyclic quadrilateral. It's the fact that the angles in the cyclic quadrilateral, the opposite ones add up to 180 degrees, don't they? So that one and that one together make 180, and the other two make 180. Okay, so in order to show that this is not a cyclic quadrilateral, we're going to have to find all the angles and show that the opposite ones do not make 180 degrees. Okay, now one angle is given as a number down here, it's 92, but the other three are given algebraically. Okay. Now we know that the sum of the interior angles of a quadrilateral add up to 360 degrees. Well, you should know that. A quadrilateral is made up of two triangles, each triangle 180, two 180s, 360. So if I take the the four angles and add them together, it should give me 360 degrees, and in which case I can then work out what the x's are then. Okay, so I'm going to use the fact that my four angles, 4x plus x plus 36 plus 5x plus 30 plus 92 equals 360. Okay, they all add up to 360. Okay, so let's just collect like terms. I've got a 4x, an x, a 5x, and that's it. And then I've got a 36, a 30, and a 92 that I need to add up. So 4x, x, and 5x, that's going to give me 10x. 36 and 30 and 92, what's that? 66, 156, 158 plus 158, and that is equal to 360 degrees. Taking 158 away from both sides, what's that give me? So it's going to be 10x on this side. 360 minus 158, that is going to be 202, isn't it? And so x then is 20.2, I suppose, degrees, 20.2. Okay, so given that x is 20.2, then 4x is going to be 4 lots of that. That's going to be 80.8 then, isn't it? Okay, so this one up here is 80.8. Okay, so can I add 80.8 to 92 and make 180? No, I cannot, and that is why this is not a cyclic quadrilateral. I can say if cyclic, then angle A plus angle C equals 180, but what I have got is 80.8 plus 92, that's 172.8 then, isn't it? Which is not equal to 180, therefore not cyclic. think some of my work here might have pooped off the edge of the screen there. Let me just kind of shift it over a little bit so you can read it. Question 29. A, B and C are 3 points on the circumference of a circle centre O. BD and CD are tangents to the circle. ABDC is a kite. Angle BDC is equal to x. Prove that angle ABO is equal to 45 minus x over 4. Okay. Right, now there's a lot of blurb above the diagram. I'm quite particular. I like to go through all of this and just double check it's on the diagram, because not always so. So BD and CD are tangents to the circle. Okay, so what does that mean? Okay, so we've got BD, these are tangents here, look. Okay, that means that that angle there must be a right angle, and that angle there must be a right angle, because of tangents are perpendicular to radiuses drawn at the point of contact. Okay, and then I've got ABDC is a kite. Now that means that that side and that side are equal in length, and that one are as well. Okay, so that also means that we can, well, I don't know what it means. Let's find out what it means in a bit. And finally, angle BDC is x. Now that has been marked on the diagram. Now we want to prove that angle ABO is something. Where is ABO? ABO is that angle there. Okay, so eventually we want to find that. Okay, now with most of these problems though, that is not your starting point. Okay, your starting point is going to be a long way away from that. Okay, all right, so what can we start with? I would start with the things that we know about. So I actually know about this angle here, x. Now I know that x, and I said earlier that I put two right angles on. I suppose we should, if we're going to prove it, we need to write that down. Okay, I'm going to say that OBD and OCD are right angles, and the reason I know that, because I'm going to give reasons for everything, is tangents are perpendicular to radius drawn at point of contact. Okay, so it's good to write down the reasons. Okay, so I know that they're right angles, and I know that OBDC is a quadrilateral. So it's angles sum to 360 degrees. Okay, so I know x, I know 90, but I don't know BOC. So angle BOC, that's got to be equal to 360. Okay, so I know that 90 and 90 is 180, and I take that away from 360, that's going to leave me with 180. So angle BOC then is going to be 180 minus x, just simplifying that down a little bit. Okay, so I know that that angle there is 180 minus x. Now I also can see that that is the angle at the center, and this one here is the angle at the circumference, isn't it? Okay, so I know that these two are related. I'm going to use the fact then that CAB is going to be a half of angle BOC, which is a half of 180 minus x. Okay, which is multiplying out the brackets, that's 90 minus x over 2. Okay, I've kind of got halfway then, isn't it? I've kind of got halfway to where I need to get to. So CAB is equal to 90 minus x over 2, and the reason for that is that angle at the center is twice the angle at circumference. Okay, so that's that. So now I know that that must be 90 minus x over 2. So then how can I find that one over there then? Well, I suppose it's got to do with the fact that ABDC is a kite, because that means that that angle and that angle are equal to each other, and we can use the angles inside the kite add up to 360 to take away the two ends and then divide it out between those two angles then, can't I? So I can say that in kite ABDC, okay, so I know the two ends, don't I? X and 90 minus x over 2. Then so I can say that ABD, angle ABD, is equal to angle ACD, because it's a kite, and angle ABD plus ACD plus CAB plus BDC must be 360, because it's a kite. It's a quadrilateral, isn't it? Okay, so what do we know there? ABD we said was 90 minus x over 2. That's ACD is equal to ABD, so I'm going to just replace that as two lots of ACD then, because they're both the same. And then BDC I know is x, and that's all equal to 360. Just going to scroll this up a little bit because I'm running out of space. Okay, so what now then? So I've got 90 minus x over 2 plus x, so that's going to be 2ACD plus 90. So minus x over 2 plus x is just going to be plus x over 2, and that's equal to 360. So taking 90 away from both sides, I'm going to, and the x over 2 away from both sides, I'm going to get 2ACD is equal to 360 minus 90 is 270 minus x over 2, and then dividing it by 2 then ACD, just one lot of ACD, is just going to be half of 270, which is 135, minus half of x over 2, which is x over 4. Okay, but if you remember, ACD is equal to OBD plus ABO. Okay, so our 135 minus x over 4 is going to be equal to OBD, which was a right angle, 90, plus ABO, which is the thing we're trying to find, isn't it? ABO. Okay, so then taking 90 away from both sides, that is going to give me 45 minus x over 4 is equal to ABO then. Okay, okay, so that was quite a long proof, but prove it we did. Okay, so very good. So ABO is 45 minus x over 4. So just running through that again from the top, we used the fact that tangents and radius is at right angles to find those right angles. Then we used the quadrilateral OBDC to find the angle at the center, and then once we had the angle at the center, we found the angle at the circumference, that's at A, and then we used the kite to find ABD, and then we took away 90 and we found ABO. Awesome, good job. Let's move on. Well, I hope this video helped you get a better overview of the topic. If it did, give it a thumbs up. You can find more exam question compilations over here. For more past paper walkthroughs, click down here. If you want to visit my Amazon shop with my recommendations for calculators, revision guides and other maths related stuff, click down here. Good luck in your revision and in your exams, and see you again next time.